This video is going to cover the background of several formulas needed to differentiate sine and cosine functions. All of these formulas that I'm going to go over in this video are going to be necessary in the next video on integrating sine and cosine functions using the method of substitution of rational functions. So I'm just going to write here, these is like our prerequisite formulas. And this is just going to be the angle addition formula. So I'm just going to go over an outline. I'm not going to do a full geometric proof. Let's see. So the angle addition formulas, we want to decompose sine of two angles, alpha plus beta. We want to decompose it into sine alpha times cosine beta plus cosine alpha times sine beta. In order to do that, I wrote this geometric construction over here. Okay, so I'm just going to label some points here. The origin point will be A, and then this point here will be B, such that AB is the ray, this ray here. And then there's going to be a perpendicular line segment drawn to the first ray. And also I'm going to draw another line segment perpendicular to the x-axis from the point B. And then I'll draw a parallel line segment parallel to the x-axis and intersect that from this point here. I'll call it E, and the point here will be C. So I'll just label each important point. So A, B, C, D, E, and F. Okay, and then we're going to talk about sines and cosines of these angles with respect to the different line segments and see if we can change them around to fit the form we're looking for. Okay, so sine of alpha plus beta is the length of the line segment, BD, divided by the length of AB. And I can rewrite the length of BD as the sum of these two lengths here, BC and CD. And instead of CD, I'm going to use the length EF. If we see, I'm not going to do a full geometric proof, but EF is the same length as CD. This is just meant to be an outline, kind of a reminder. Okay, so now I have, instead of BD divided by AB, I have the sum of these two line segments, BC divided by AB plus EF divided by AB. Right, now the trick is going to be to express BC, the ratio BC over AB, as a multiple of two different ratios involving the sides of these right triangles that we see here. So we see this is a right triangle here, but the right triangle we want to pay attention to is going to be actually BCE. So if you notice, this angle here is going to be alpha as well, because alternate interior angles of since we have two parallel lines and we have an intersecting line, the alternate interior angles are equivalent. And then this angle here is also going to be alpha as well, since this is a right triangle and we have these two angles here are common, so they have to add up to be 90 degrees as well. And so the two acute angles in a right triangle add up to be 90 degrees, since these two angles add to be 90 and these two angles add to be 90. I can subtract that one out, and we see that these angles must be the same. So these are all similar right triangles is what I'm trying to say. And what I mean by that is we can see AFE is a similar right triangle to BCE. Okay, so just wanted to make sure I mentioned that. And so instead of BC divided by AB, I'm going to say BC over BE times BE over AB. And I'll just write it out algebraically so we can see how that works. So it's BC divided by BE times the length of BE divided by the length of AB. So now we can see that these two lengths of BE are just divided out. So these two terms here, or this expansion, is equivalent to the previous line up there. And then I'm going to do something similar here. Instead of EF divided by AB, it'll be EF divided by AE. Times AE divided by AB. Alright, and now I can express each of these as a sine or a cosine, since these all have to do with the right triangles here, the similar right triangles. So BC over BE is going to be the cosine of alpha. BE over AB is the sine of beta. And then that's going to be plus EF over AE. EF over AE is the sine alpha. And AEAB is cosine beta. AE divided by AB. Right, and then I'm just going to flip it around. This will be sine alpha cosine beta plus cosine alpha. So this is a pretty common proof. Probably most will remember it from their geometry course or maybe trigonometry. So similarly, I can show kind of the same thing with the cosine alpha plus beta. I'm not going to explain it this time. I'll just work it out really quickly so we can move on to the next portion of the video. But we start out with the cosine of alpha plus beta is AD divided by AB, and instead of AD I'm just expressing that as AF minus DF, and then instead of AF minus DF I'm going to have AF minus CE. Since we're talking of lengths, that's why I can make these substitutions here. Instead of DF, I can use CE since they're just the lengths. Okay. I really just included this kind of for completeness sake. This is really just an outline of a more in-depth geometric study of this figure here. But really quickly, I wrote AF here divided by AB, which decomposed into AF divided by AE times AE divided by AB. So we can see that the ratio AF over AE times AE over, or the ratio AE over AB is the same as that original ratio AF over AB. And then we needed to subtract out a similar thing here, CE over BE times BE over AB, which we can see we use the cosines and the sines of the angles that are shown here on the diagram. Okay, so just going to move on from this. So we're going to use this fact in the next video, the next page on, or the page after this page. I'm going to talk about limits really quickly, and then we're going to use these two formulas plus our limit formulas to talk about the derivative of sine and cosine. Okay, so let me see. Actually, I'm just going to use this page. Alright, this is going to be important limits. And this here is a unit circle. So if I draw a sector of this circle with the point here, we'll say that point is A, which is going to be the cosine theta, sine theta of this angle theta. And then if I draw this line segment here, the length of which will represent the sine of theta. And that means that this point here, the length along the x-axis represents the is represented by cosine of theta, the length of it. Okay, and then let's imagine I have another circle with the cosine of theta being the radius here, or I'll just draw the sector inside this triangle of that smaller circle. Okay. Alright, and then I'm just going to label some important points here. This will be B, this point here will be C, and this point here will be D. Okay, and just a reminder, C is cosine theta 0, B is 1, 0, and A is cosine theta, sine theta. And we could also describe what D is by, but I'm not going to get into that. That's not important for this this video. Alright, so a couple of things to note is if we want to find the area of a sector of a circle, meaning if I have the sector A, and this will be, I'll just call this O for origin point. If I have a sector AOB, then if I wanted to find the area of that sector, I would need to find out what theta was, and then I could find the ratio of theta to so theta is an arc measurement along AB, the length of the arc that corresponds to the angle. So if I want to divide that by the full arc, which is 2 pi, then the ratio of the area to the sector to the area of the entire circle would be theta divided by 2 pi. So I could take that ratio and multiply it by the area of a circle, pi r squared, to determine that the area of the sector is going to be, the pi will divide out, and I'll just have 1/2 theta, the arc length, times r squared. So this is the formula for the area of a sector. And another thing to note is that the sine of theta, meaning this length of the segment here, AC, is going to be less than the arc length, theta. I think that's kind of obvious. I'm not aware of how to prove it right now. I'd probably go back and study some more. But I've always just looked at it and I said, okay, that's an obvious fact, that this line, the straight line here, is less than the arc, no matter where that point is. Even if it's over here really close, we still have a curved line and then a straight line. So I'll just leave that as kind of an obvious thing to see. There probably is some more in-depth proof in the realm of analysis of geometric figures or something like that. But from this fact, it follows that the sine of theta divided by theta is less than 1. And this is important for our limits. And I'm going to make more videos talking about limits in more depth, but we're going to take for granted a few facts about limits in this video. So one of those being the squeeze theorem, and I'll talk a little bit about it right now. But anyways, so let's talk about the limit formulas that are going to arise when we apply our formula for the derivative to sine and cosine functions. So that the limit formulas, the important ones that we need to know, are going to be, they're going to come from the fact that the area of the sector, we'll call it COD, sector COD, is less than the area of this triangle here, the triangle COA, which is also less than the larger sector BOA. Okay, so what I mean is the smaller sector here that we drew is has an area that's less than the area of the triangle, which has an area that's less than the sector of the unit circle. All right, so I can write the area of the sector using our formula for sector. So COD has a radius of cosine theta, so I'll go ahead and write this is going to be 1/2 theta times the radius, cosine theta squared. That's the area of that sector, and that's less than the area of this triangle, which is 1/2 times the width times the height, or cosine theta times sine theta, which is less than the area of the sector BOA, which is our sector of the unit circle. The unit circle has radius 1, so it's just going to be 1/2 theta times 1 squared. Alright, let's see if I can simplify this. I can divide out 1/2 theta cosine theta to each of these. Alright, so here I'm left with cosine theta is less than, so 1/2 and cosine theta divide out, so here I have sine theta divided by theta. And the reason I divided that out that way is because I know sine theta divided by theta is less than 1. So I'm just going to write is less than 1 on this side, because I'm just using the first part of this. This would actually be 1 divided by cosine theta, which is greater than 1, so I can see that this is actually bounded by 1 by this fact here, rather than 1 divided by cosine theta, which we don't need that to be bounded by that. Okay, so what I mean by bounded is, I mean this function, sine theta divided by theta, is always going to be greater than cosine theta, and it's always going to be less than 1. So if I can show that the closer my theta gets to 0, by properties of limits, mainly the squeeze theorem, if cosine of theta, if its limit as theta approaches 0 is 1, and I know that this is bounded by 1 as well, so that must mean that the limit of sine theta divided by theta as theta approaches 0 is 1 as well. So I'm going to go ahead and write that. I'll say the limit as theta approaches 0 of cosine theta is less than, so I'll write up parentheses, the limit as theta approaches 0 of sine theta divided by theta, which is less than 1. The limit as theta approaches 0 doesn't change a constant number. It's always less than 1. And I know this limit is going to be 1 because I can evaluate cosine of theta at 1. The reason we can't evaluate this limit is because it's divided by 0. So the way limits work, and I'll just touch on this, I know I'm going to explain it in other videos as well, but our function that we're evaluating the limit at, the number that we're evaluating the limit at for the function, if it's continuous at that number or a neighborhood around that number, then we can evaluate it at that number, then that's what the limit equals. But if it's not continuous at that number, in this function here we see we can't divide it at 0, so it's not actually continuous at that number. We have to use other functions and its relation to other functions to figure out what's happening there. So that's why we use the squeeze theorem here. So I guess I can say by squeeze theorem. And I know this is 1 is less than the limit as theta approaches 0. So this implies that the limit as theta approaches 0 of sine theta divided by theta is equal to 1. All right, and this is the important limit formula that we need. And then I'm going to use this fact to talk about the next limit formula we're going to need, and that's the limit as theta approaches 0 of 1 minus cosine theta divided by theta. All right, so this one we can derive algebraically using the last limit formula. So this is going to be 1 minus cosine theta, and I will multiply that by 1 plus cosine theta divided by 1 plus cosine theta. I'm sorry, that's divided by theta. And the reason we can't evaluate this function here is because we're dividing by theta again. So it's not continuous over the limit, the number we're evaluating the limit at. Alright, so here we're going to have the limit as theta approaches 0 of 1 minus cosine squared theta, and theta times 1 plus cosine theta. So just write it here. Alright, so this is actually going to be sine squared theta divided by theta times 1 plus cosine theta. And so I can actually split this up into, so the limit of two multiples of two functions that are being multiplied together is the limit of those functions. So this is something that can be done. I can take that sine theta divided by theta, take the limit of that function, and then multiply it by the limit, this function, sine theta divided by one plus cosine theta. Alright, so now if you notice, we can actually take the limit of this function here, because this is going to be, feels like I messed up on something. This one is going to evaluate to be 0, because sine of theta is continuous over the interval around the neighborhood around 0. So, and 1 plus cosine of theta will, that we can also evaluate that. So this gives us a number. This function is continuous over that interval, and we can evaluate it at the 0 here, the value 0. So that means the limit of that is just what this function evaluates to at that point, or at the number 0. And then we know this limit as well, that's 1. So this is going to be 1 times, and sine of 0 is 0. So 0 and 1 plus cosine of 0 is 2. So it's just 0. So now we know this limit. The limit as theta approaches 0, 1 minus cosine theta divided by theta. And like I said, I'm going to talk about limits in more depth as well. I guess I'm working backwards. I wanted to start talking about trig functions and their derivatives and integrals. And so that's why this is going to build up to the video where we differentiate trig functions using substitution of rational functions. So this is kind of a big step back, I guess, to covering the derivatives of sine and cosine, which will be what this page talks about. So derivatives of the functions sine x and cosine x. So by the definition of a derivative, if I take the derivative d dx of this function sine x, by definition it's going to be the limit as this value h approaches 0 of sine x plus h minus sine x divided by h. So this is where the angle addition formulas come in handy. So we can't really do anything with this limit right now until we can reduce it to a form that gives us an answer, that gives us limits that we can evaluate. So we're going to use the angle addition formula, and then we're going to do some algebra on this inside term here until we uncover the forms that I showed you in the previous 2 pages, those limit formulas. Alright, so this is going to be the limit as h approaches 0, and we'll use the angle addition formula. This is going to be sine of x cosine h plus cosine x sine h minus sine x, all that times h. And here, the first term and the last term in the numerator, we can factor out a sine of x. It's going to be sine of x times cosine h minus 1. And I'll go ahead and separate the terms. So if I have 2 functions and I'm taking the limit of those 2 functions, g plus h, and I'm taking the limit of g plus h, I can take the limit of g plus the limit of h. That is a property of limits. So this Alright, so we're almost to the point where we can see these limit formulas arise. So this is sine of x, it's not affected by the value of h, so I can take it to the outside of the limit. It's effectively a constant, and same with the cosine of x. So this is, and I'm also going to factor out a negative in the numerator so that it changes form a little bit. So this is actually going to be negative sine x times the limit as h approaches 0 of 1 minus cosine h divided by h. And then I'm going to do the same thing over here, factor out a cosine x times the limit as h approaches 0 of sine h over h. So if you remember from the last video, this limit evaluates to 0 and this limit evaluates to 1. So this entire term is going to go away. It's multiplied by 0, and this is multiplied by 1, so we see we're just left with cosine x. Alright, Alright, so that is the derivative of sine x. And I can do the same thing with cosine x. I guess I'll go ahead and show it. So it's going to be the limit as h approaches 0 of cosine x plus h minus cosine x divided by h So we use the cosine angle addition formula to expand it. And then we'll change the form around a little bit to uncover those limit forms. I can factor out a cosine x here. That's cosine h minus 1. So it looks very similar to the last problem. Then I have minus the limit as h approaches 0 I'm going to do something similar the last time. I'm going to factor out our negative cosine x, multiply that by the limit, and we'll leave everything with an h term inside, and that's 1 minus cosine h divided by h. So I factored out the negative. Instead of cosine h minus 1, it's 1 minus cosine h, and minus the limit as h approaches 0. Oh. I can factor out the sine of x. It's essentially a constant with respect to the limit as h approaches 0 of sine h divided by h. So this is 1, this is 0. So we can see that we're going to have a negative sine x left. Okay. So I'm going to end here. I'm not going to talk about the inverse trig functions right now in the derivatives because I want to leave that for a whole other video. It has a lot of applications, but that is the only other, I think the only other formula that I used when talking about the method of substitution. It will be in the next one of the next videos in this series.